Now this next beam is again a cantilever beam having a uniformly distributed load acting up to a distance of A from the point A, and the whole length of the beam is L. So we have to find the slope and the deflection at the free end. So as we did in the previous questions, first we will draw the elastic curve. So the elastic curve will be something like this. This green curve which you are observing here is the elastic curve. Now we will draw the tangents at the relevant points. So tangent at A will be straight like this because A is fixed, so there will be no deflection, or sorry, there will be no rotation here. Then tangent at B. So as you can see in the portion CB there is no load acting, so here the BC portion is straight line, right? In the elastic curve of this, or the deflected shape of this beam, due to the loading, the AC portion is loaded, so therefore it will be a bit curved, and CB portion is not loaded, so it will be inclined, straight inclined, right? So due to B, tangent at B will coincide with the curve. So as you can see, this black line showing here is the tangent at this. So tangent at B and C will coincide with this BC portion. Okay, so according to this, it is clear that our theta or slope at B will be equal to slope at C, right? And this is the TBA, vertical distance of the point A from the tangent at A, right? So we want to calculate theta B, so we can easily calculate it by using the moment area method. Now we will draw the M by EI diagram. So first, this is the bending moment diagram. As you can see, in the portion AC only, because there is no load in CB, and its maximum value will be minus WA square by 2, right? Now the M by EI diagram will be same, just the value we will get is minus WA square by 2EI. Okay, so for calculating the slope at B, we will use the theorem 1 of moment area method, which says that theta BA is equal to area of M by EI diagram between A and B. So between A and B, as you can see, the bending moment, the M by EI diagram is only this AC C dash. So this will be the bending moment diagram here. So we will find its area. So area of this will be 1/3 of A into minus WA square by 2EI, because this is a semi-parabola, so its area is 1/3 B into H. So we will get theta B is minus WA cubed by 6EI. We will use a second theorem, which says that, so as you can see in this figure, YB will be same as this distance TBA. YB will be same as TBA, and TBA can be calculated by using this formula, that it is equal to area of the bending moment diagram between A and B into the distance of centroid measured from B end, because we are determining TBA. So again the area will be same, minus WA cubed by 6EI. And now to calculate the distance from B, the centroid of this area G is at a distance of 3/4 B. This you know that if we have a semi-parabola and this distance is B, so its centroid will be at a distance of 3/4 of B from this end. Okay, so it will be, as here the distance is A, so it will be 3/4 of A. Okay, so the total distance from B will become 3/4 of A plus L minus A, because we want to find the location of this centroid from the end B. So the X bar will become L minus A plus 3A/4. So this will be the equation for YB which we get, right? Now we will take the next question. So till now we have studied only about the cantilever beams. Now we will take the case of a simple support beam, 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 which is acted upon by a point load acting at its center, right? So how do we calculate its slope and deflection? So here you can see that we have to find theta A, theta B, theta C and YD. So A and B are the ends of the beam, simply supported beam. D is the middle point and C is a point at a distance of L by 4 from D. Okay, so we have to find slopes at these 3 points A, B and C, and we have to find the deflection at D, right? So first we will draw the elastic curve. So now this is a simply supported beam. So in simply supported beam, in both the ends rotation cannot be 0, right? So it will not be equal to 0. So the deflected shape will be something like this, and it will be a symmetrical deflection because the load is acting at the center and this is a symmetrically loaded beam. So this is the elastic curve for the beam, right? Now I will mark these points. This is point A, B, the center point C, and this is the point C. Okay, center point is D. So I have marked these in the elastic curve. Now I will draw the tangents, right? So tangent from A will be something like this. Tangent at B, then tangent at C, and the tangent at D will be horizontal. Now why I have taken this tangent to be horizontal? This is because this D point is at the center of the beam, and because this beam is symmetrically loaded, therefore we can conclude that there will be maximum deflection at D point. Okay, so wherever there is a maximum deflection, we will get the slope to be 0 because the curve will be straight here. So the tangent will also be straight. Okay, so this is our tangents. Now I will draw some angles here. So this is tangent D and this is tangent A, right? So the angle between these two is theta dA, right? This is my tangent D and this is tangent B. So angle between these theta BD, tangent C and tangent D, theta CD, right? Now why I am making all these angles with respect to D with respect to tangent D, I have shown this angle of tangent A from D, then of tangent C with D, then tangent B with D. So why I have taken D as the relative tangent? This is because if you remember when we were studying cantilever beam, this is A and B. So if I want to calculate theta B, then I use the relation theta BA is equal to area of m by a diagram between A and B, because this can be written as theta B minus theta A, right? So why I used theta A as the relative point? Because we know that theta A will be 0 always, because this is a fixed end, right? So because we have to find out theta B, we need to be sure about the value of theta A by so that we can calculate the value of theta B by using the relation this, right? So to conclude, we must know the value of the theta at the second point. Now consider this simply supported beam here. If I want to calculate theta at B, and if I use the same relation theta BA, and I write it as theta B minus theta A. So now if I want to find out theta B, I use the same equation, area of m by A diagram between A and B. But in this case, theta A as well as theta B are both unknowns, because these are not equal to 0. So we have to choose that point, the second relative point, whose values we are sure about. So in this whole simply supported beam, we are sure of one thing, that theta D will be 0, because the deflection at D will be maximum. In this case only, because this is a symmetrical loaded beam, so we are sure that the load will be maximum at the center. So sorry, the deflection will be maximum at the center, so slope will be 0. So if I want to calculate theta B, then I will use this relation, theta BD is equal to theta B minus D, and I will put theta D is equal to 0. So that's how I will be able to find out theta B, right? So that's so when in this question, when we want to find out theta A, B, C, then we have to choose D as the relative tangent for all these points. Okay. So now we will proceed. So we have to, the next step for this is, after we have understood the elastic curve and the different tangents, then we will draw the bending moment diagram, right? So as this is a simply supported beam, we can say that moment at A will be 0 and moment at B will also be 0, right? And moment at D will be, because these are the reactions RA and RB, which will be P by 2, P by 2. So we can say that moment at the center, which is D, will be P by 2 into L by 2, that is PL by 4, right? And if I want to find out MC, that is moment at this point, so it will be P by 2 into L by 4, because this distance will be L by 4, so it will be PL by 8. Okay, so now we will draw the bending moment diagram. So the bending moment diagram will be like this. So if this is A and D, now these two values are 0, value at D will be maximum, right? And we will connect it like this with inclined lines. So value of this point is PL by 4, and at C is PL by 8, right? So this is the bending moment diagram. Draw the M by EI diagram. So just we will divide the values by EI. So this will become PL by 4 EI, and it will be PL by 8 EI. This is C dash, this is D dash. Okay, so this is the M by EI diagram. Now we will start with the calculations. So first I am calculating theta at C. So I have already explained to you that for calculating theta at C, I will obviously use theorem 1, And theorem 1 says that this angle will be theta c minus theta d, which will be area of m by ei diagram between c and d, right? So theta d will be 0, right? So theta d will be 0. So we can say that theta c is equal to area of m by a diagram between c and d. So see here the m by a diagram. So between c and d we have this trapezium c, c dash, d dash, d. Okay. So this is trapezium. So the formula for area of trapezium is it is half sum of parallel sides into the vertical distance between the parallel sides. So it will be half into parallel sides are CC dash and DD dash, and the vertical distance between them is CD, right? So CC dash is PL by 8 EI, DD dash is PL by 4 EI, and CD is, you can see here in the loading diagram, CD is L by 4. So after solving it, we will get theta C as 3 PL by 64 EI. Okay, so this is positive because the slope is ascending, as you can say, at this C point, right? Now similarly we will calculate theta B and theta A. So for calculating theta A, I will take theta dA as the angle, which is this angle. So this will be theta d minus theta A, and it will be equal to area of m by ei diagram between A and D, right? So here also theta d will be 0. So we will get minus theta A is equal to here see this m by a diagram. So between A and D, this is the area, this is a triangle, area of triangle A D D dash. So it will be half into AD into DD dash. So AD is L by 2, DD dash is PL by 4 EI. So therefore theta A will be minus PL square upon 16 EI, right? A will be minus PL square by 16 EI, and minus sign indicates that see this at A the slope is descending, right? So this is the meaning of this negative sign. Now similarly we can calculate theta B. So theta B will be theta BD, that is theta B minus theta D, which is area of m by ei diagram between B and D. So again theta D will be 0, so we will be left with theta B, and area of, so look at this triangle between B and D, we have this triangle BD D dash. So area of BD D dash, which will be equal to half into BD into DD dash. So we will get half into BD is L by 2 and this is PL by 4 EI. So L by 2 into PL by 4 EI. So the same value as theta C. So theta B will be, sorry, theta A, which is PL square by 16 EI. Just the sign will be positive here. Okay. Now we want to calculate the deflection at D, right? fourth is deflection at D. So I will again draw the elastic curve for this. So this was the elastic curve. This is A, B, D and C, right? So what do I want to calculate is I want to calculate this, which is YD. So how to find this YD? So you must be clear on this that the moment area method does not give you the equation to solve the theta or y directly, but it gives you the equation to solve these two values indirectly. Like, see here, when we want to calculate theta b, we used theta bd angle, which is theta b minus theta d, right? Similarly, in the cantilever questions, when we were calculating yb, like this is b, then yb was same as tba, right? So we use the equation yb is equal to tba to moment of area, okay, whichever theorem number 2. Now in this case we cannot use it directly. Yd, we cannot say that yd will be same as why we cannot calculate yd directly. But we know this one thing, see here carefully. So we have to use the moment area method and this elastic curve according to our need. So I want to calculate this distance. So for that, first I will draw this tangent at D, and this is tangent at A. Okay. So if I mark this distance here, what is this distance giving me? See this point, this is point A, and this is the tangent line at D. Right? I will show it again. This is my point A, and this line is tangent D. So what does this distance signify? This distance means the distance or vertical deviation of point A from the tangent at D. So we can write this as vertical deviation of point A from tangent at D, right? And if you look at this figure, as this is symmetrically loaded, so we can say that this TAD is same as YD, right? So therefore we can say that YD is equal to TAD, right? In this, if you see this picture, so we have to devise and we have to identify this relation ourselves in the beam depending on our type of beam and the loading and which values we want to find out. So TAD, okay. So now I can use, now I know from moment area theorem 2 that the relation for this TAD. So what is that? TAD is the area of M by EI diagram between A and D into multiply by sorry, multiply by distance of centroid of the area from point A, because we are determining TAD, so we will take distance from point A, right? So I will draw the M by A diagram first. So this is our M by A diagram. This is A, this is D, this is D dash, and this value with the maximum value which we calculated was PL by 4EI. Okay, so and the centroid will be here. So we want to find the distance of centroid from point A, and this whole distance is L by 2, AD is L by 2. So this distance AG will be 2 by third of L by 2, right? In a triangle, if we have a triangle like this, then this distance of CG is L by 3 and this is 2L by 3, right? If whole of this base is L. So now our base is L by 2, so we will take this to be 2 by third of L by 2. So YD will be area of M by D diagram between A and B will be half into L by 2 into PL by 4EI into 2 third of L by 2. Right? You must be very clear about this, that we are finding DAD, so we have to take distance from A and not D, right? And I have already explained to you what is TAD. TAD is equal to YD, that's why we are calculating TAD, not DDA. Okay. After solving this, we will get PL square by 16 EI into L by 3, right? 2 and 2 will get cancelled here. So we will get QL, which is the deflection, deflection at the center of simply supported beam acted upon by load acting at its center, right? Similarly, if you have understood this clearly, you can calculate or determine the vertical deflection or slope at any other point also. If we want to find out, for example, if we want to find out YC, so we have to establish a relation between YC and any this either TCD or TAD or TBD, any of these according to our suitability, and we can find out C also, right? So this is how moment area method is used for simply supported beams.